AKS, a practical beginner mental model. Welcome. In this pilot episode, we will build a practical mental model for Azure Kubernetes Service, usually called AKS. The goal is not to make you production ready in a few minutes. It is to give you a map. By the end, you should understand what Azure manages, what Kubernetes manages, and what still belongs to you. Why AKS exists. A container image packages an application with the files and runtime dependencies it needs. Starting a container is useful, but a real service needs more. Which machine should run it? What happens when it fails? How do we run several copies? How does traffic find a replacement? How do we roll out a new version safely? Kubernetes answers these questions through an API and a set of control loops. You declare a desired state, such as 3 replicas of an application. Kubernetes keeps comparing that desired state with reality and takes action when they differ. Kubernetes itself has a control plane. It stores cluster state, receives API requests, schedules work, and runs controllers. If you operate Kubernetes yourself, you also operate and secure those components. With AKS, Azure creates and operates the managed control plane. You use the Kubernetes API, but you do not normally manage control plane virtual machines. You still choose worker capacity, networking, identities, policies, application configuration, updates, and operating practices. Managed, therefore, does not mean responsibility-free. It means the responsibility boundary has moved. There is a matching cost lesson. A free cluster management tier does not make the worker machines free. If worker nodes remain allocated, an idle learning cluster can still cost money. The architecture mental model. Picture an AKS cluster as 2 cooperating areas, an Azure-managed control plane and 1 or more node pools. The control plane exposes the Kubernetes API. The scheduler chooses a suitable node for new work. Controllers compare desired and observed state and try to correct differences. A node is a worker machine where application containers run. In AKS, nodes are Azure virtual machines managed in groups called node pools. Nodes in a pool share important configuration. Separate pools can support different workloads, operating systems, virtual machine sizes, or scaling behavior. Kubernetes normally schedules a pod, not a bare container. A pod is the smallest standard scheduling unit. A simple pod often contains 1 application container. Closely coupled helper containers can share the same pod network and storage context. A pod should be considered replaceable. Do not design around 1 pod name or IP address living forever. A deployment describes how a stateless application should run. It contains a pod template and a desired replica count. If a pod disappears, the deployment controller creates a replacement. When the image changes, the deployment can roll out the new version. A service gives a changing group of pods a stable network identity. Labels and selectors connect the service to the right pods. Depending on the design, the service may be internal, or it may sit behind an ingress or gateway for external HTTP traffic. Here is the relationship to remember. Azure operates the managed control plane. Node pools provide worker capacity. The scheduler places pods on nodes. A deployment maintains the desired pods. A service gives those replaceable pods a stable destination. From image to application. A safe deployment begins before Kubernetes. Build the image reproducibly, scan it, and push it to a trusted registry. Use an immutable version, or digest when repeatability matters. Next, submit a deployment manifest. The pod template names the image, ports, configuration, and resource settings. Start with realistic CPU and memory requests. Requests help the scheduler decide where the pod fits and give scaling systems a meaningful picture of demand. Add health probes carefully. A readiness probe asks whether an instance should receive traffic right now. A failing readiness probe can remove the pod from eligible service endpoints. A liveness probe asks whether the container is stuck and should be restarted. An aggressive shared test can turn a slow dependency into a restart storm. Create a service for stable discovery. Begin with internal exposure unless public access is genuinely required. Public exposure affects security, certificates, DNS, routing, and cost, so it deserves a deliberate design. Apply changes declaratively and watch the rollout. Check deployment status, pod events, container logs, and service endpoints. The API accepting a manifest does not prove that the application works. An image pool can fail, a health probe can be wrong, capacity can be unavailable, or the application can exit. If a revision is unhealthy, pause or undo the rollout. Versioned images and manifests make recovery far easier than improvised changes. Operate safely. Identity becomes clearer when you separate three questions. First, who can administer the cluster? Use individual Microsoft Entra identities and properly scoped Azure and Kubernetes permissions instead of shared administrator credentials. Second, how does AKS manage Azure resources? The cluster uses a managed identity for its platform operations. That is not automatically the identity of an application. Third, how does a pod access an Azure service? Microsoft Entra Workload Identity lets a Kubernetes service account use federation, avoiding a stored application secret. Give each workload only the permissions it requires. Scaling also has separate loops. A horizontal pod autoscaler changes the desired number of pod replicas. Cader, pronounced Cader, can scale pods from event sources. Node scaling changes the worker capacity available for those pods. More replicas cannot run if no node has space. More nodes do not automatically change the number of application replicas. Resource requests connect these decisions. Observability should answer questions. Begin with application success and latency, pod restarts, resource saturation, pending pods, node health, deployments, and important events. Central logs help, but collecting everything forever can become expensive. For a learning cluster, control cost through lifespan. Use clear resource group names and tags, create a budget alert, choose modest capacity, and delete the lab when finished. Remember attached disks, public addresses, load balancers, registries, and monitoring data. Recap. AKS manages the Kubernetes control plane and integrates the cluster with Azure. Your worker capacity, applications, identities, and operating choices still matter. Node pools contain worker nodes. The scheduler places pods on nodes. Deployments maintain replicas and roll out changes. Services provide stable discovery for replaceable pods. Your next lab can be small. Create a short-lived cluster. Connect with Kube Control. Deploy a version sample image through a deployment. Expose it internally with a service. Inspect the rollout and logs. Scale the replicas. Then delete the resource group and check the cost. That is enough to turn the mental model into something you can observe. Thanks for listening.